Cool. Hi, folks. Can you all hear me? Awesome. Okay, welcome back from lunch. I do have the inauspicious honor of going directly after lunch, where everyone's probably already just wanting to curl up in a ball and digest. So I also acknowledge that you've been here for a very, very long time with your bums in these seats and then staying out very late. So your cognitive batteries are probably exhausted, your social batteries are probably exhausted. So with all this in mind, I am going to show you 0 equations, I'm going to show you no math, and I'm mostly going to show you probably cool images and videos. Go. Okay, cool. Okay, this makes me feel like I planned this talk correctly, despite my inclinations. Okay, awesome. So the other thing is that I have to dispense with, honestly, this really crappy title. I apologize. I'm not really going to talk about exactly this, partly because I was a little too lazy just to send the organizers a better title, but also because it is late in the week, and so instead of trying to drill down into technical topics, what I'd really like to try to do today is to instead communicate one research design pattern, a really high-level topic where maybe I can help show you one way you can conduct really ambitious research in all the fields that have been discussed this week, and do so in a tractable way that carves out nice incremental progress that you can landmark, milestone, and hopefully will get you a great job someday. I can't promise the last bit, but I can promise to share with you one design pattern. So is everyone okay with that if I sort of go a little bit off the technical stack and instead try to talk a little bit about how to do ambitious research? Okay, cool. Great, that makes me super happy. So with that in mind, I think we've all been talking a lot about this particular topic on the screen, so I'm going to retitle my talk The Thing That Comes After This. And in fact, I think that really what I'd like to do is use the next thing, the next topic, and I'm just going to do this right now. Ooh, fancy. I'm going to use this particular topic as a lens to think about ambitious research in machine intelligence, and this topic is, in fact, intelligence amplification. I don't know if any of you heard this, maybe show of hands. I won't do too much interactive stuff. Okay, a couple of you have seen this, more, maybe a dozen. That's fantastic. Intelligence amplification. So if we acknowledge the fact that really AI didn't start in like 2012, much to my common opinion, maybe it did. But if we go back to those musty old books in the 1950s, you'll see work by like W. Ross Ashby talking about intelligence amplification, or the use of technology, the use of intelligent systems as a way to amplify human ability to choose or decide, to increase the number of options we can consider and the way that we can consider those options. So I'm going to use IA for you today, not as the main topic of my talk, but as a lens by which we can view ambitious research. And in particular, I'll show you some of the research we've been doing on applied RL for robots here at the university, but with a focus on this topic. And another way to summarize this with the help from Zombie John Lennon here is really that you can think about Lego blocking together intelligent systems. You can think about amplifying the power of one intelligence using another intelligence. And I mean, maybe Rich, if Rich is around, Rich would probably be happy that I'm brokering this as part of my talk, so maybe he can build on similar ideas. But the idea that, in fact, intelligence is one of the most powerful tools we can develop as a species. And so, yes, it is possible, and in fact, it's inevitable that we begin to use that as a way to enhance or amplify our own intelligence. Cool. Okay. To get there, I'm going to start somewhere that I think is very familiar to everybody, and that's robots. This is actually a picture I took at the Toyota Museum in Nagoya, Japan. And some of my students have seen these slides before, so I apologize for boring you with the same thing over and over again. But for those who haven't, this is what we usually think about when we think about automation. We think about robots that are, putting together parts of a car, or they're like welding and soldering things, they're maybe spray painting. They're even like installing the transmission in the bottom of a car. This is usually what we think about when we think about robotics and automation. And again, this was the Toyota Museum. So does anyone know, those who haven't seen me give this part of a talk like this before, what Toyota did when they were Toyota? What they did before they did automobiles? Close. What's that? I can't hear. Scream louder. Toasters? Is that what someone said? Anyone else? Is it kitchen stuff? It's close to kitchen stuff. Okay, I'll follow on the surprise. They actually did this, textiles. So pretty close to some of the things that I was talking about. And why I bring this up, if you ever get a chance to go to Nagoya and go to this museum, I highly recommend it because it is a beautiful textbook of an incremental process of automation. It shows how Toyota and their very innovative people who worked at Toyota, especially their founder, were able to think about the process of weaving textiles, of turning particulate matter, things like plant matter and animal fur, turning that into threads, into fabrics, into textiles, and how they identified each particular piece of the system that could be improved or augmented, and then incrementally augmented it to build a system that was far more powerful than the original spinning loom. These massive systems that, like, while I was there watching, they were essentially like 3D printing textiles and fabrics, weaving 16 threads of different colors together as fast as I could watch to create, like, elegantly designed blankets. So I want to use this as a lens for our discussion today into IA, because this is an incremental process of augmentation, of amplification. Because we go from that to another step, and soon, clearly we get here. We get intelligent systems. And I think that, like, I'm only being partly cheeky here, because I do view this as one pathway to strong, ambitious artificial general intelligence, is the same kind of incremental automation of processes that we saw in the way that Toyota went from a spinning loom all the way up to automobile manufacture and very ambitious manufacturing. Okay, is everyone tracking so far? Cool, because this is what gets me to the whole point of this talk. If I have to do one thing in this entire talk, then I'm hoping that I can communicate to all of you, not the best, but one possible research design pattern that you can use to tackle ambitious real-world problems, especially in the area of machine intelligence. This is my whole goal for this particular talk, and so we're going to keep walking through this using IA as a lens. In particular, though, this is another way of saying something that many of you have probably heard me say many, many times over and over again if you've interacted with me, and that's, personally as a researcher, I never tried to storm a castle by the front doors. This seems like a really foolish thing. Sometimes it works, but often you just bang your head against a really, really strong gate. And instead, I prefer to try other things, which, I mean, this slide should really, really tell you mainly that, A, I can't draw, and B, that everything I learned about research I learned from, like, Zelda Breath of the Wild and probably watching the middle Lord of the Rings movie. But I mean it, I actually mean this, is that there's often ways to approach research problems that are not banging head-on against the hardest part of the problem, but they're incremental ways to begin to tackle research, especially very ambitious research, in domains that you might not even fully understand when you approach them. So again, let's go back to IA as a example of this. This is the research problem that you could say, if you look at all the things that I do on a regular basis, this is really what I tackle. This is the problem of Lego blocking together intelligences to create a larger intelligence, something more than the sum of its parts, is the ambitious problem that I choose to focus on. So because I'm not really qualified to talk about anything else, that's what we're going to talk about today. And I'm going to show you first, as I promised, a bunch of cool videos. And this one is playing now. Great. Who's seen this video before? Oh, okay, awesome. So maybe this is more, except for, like, those jokers up in the corner there who've seen me give, like, a dozen talks like this. All right, this is a picture of a study participant named Jan Schuurman working with the folks at University of Pittsburgh and the BrainGate project. And when I talk about IA, or intelligence amplification, one thing that I'd like to use as an example is this particular slide. Jan is a participant who is paralyzed from the neck down. So she can't move the body below her neck. And here you can see there's those two gray plugs that are on top of her head. They're actually plugs. These are electrode arrays, like a high-density electrode arrays that are implanted into two regions on the surface of her brain. And so what Jan's doing here through a range of hardware technology and software is using the patterns of her brain activity to control that robot arm to feed herself a chocolate bar, to eat silly strings, to drink things, fist bump doctors. You'll see all sorts of things if we kept the video playing. But this is just one example, and I'm going to show you a bunch in a row without really dwelling on them, of how we are starting to connect together intelligent systems to increase our ability to act or perceive the world. That sound good? Oh, I also want to mention that, again, probably some of you are, like, taking photos and stuff. I wasn't able to put these slides on my website before the talk, but I am going to put all my slides up on my personal website, my university website, so you can go download them from there. Just a PDF, so it's easy to download. And I'm going to pepper most of my slides with references. I don't expect you to read them or think about them, but I'm also planning for future you and future me where we actually care about going back and be like, oh, what was that cool thing with the brain interfaces? So I've dumped them on my slides. It causes visual clutter. I apologize, but not too much. All right, next slide. Next slide. So, okay, that was an example of chaining technology and the human body together in sort of a way where the person extends themselves out into the world. There's other people in the world, I'm thinking of, like, Theodore Berger and colleagues and the people at Kernel, who are looking at, in fact, replacing whole thinking modules. Imagine part of the brain was damaged due to injury or illness, maybe a stroke, maybe a workplace accident. What companies like this are looking at and what people like this are looking at is actually using models, computational models, deep neural models, to understand how that damaged part of brain might have actually functioned, and then replacing the missing part of an actual biological brain with a piece of technology that takes in signals from the remaining brain and spits signals back out into the remaining brain. The example they use is long-term and short-term memory consolidation, how you might build a module that would help someone take their short-term experiences and, in the absence of a functioning biological bit of their brain, turn that into long-term stored experience. So this is a case of the brain of essentially taking and sending and receiving neural signals. There's more examples. This is closer to the line of the work that I actually do on a regular basis. Upper limb prostheses, robotic devices attached to the body, in most cases attached to the peripheral parts of the body, not directly into the nerves. This gentleman here is a dual shoulder disarticulation individual. He's had both his arms removed at the shoulders. And here he's actually using two robotic limbs, two dexterous robotic limbs, to interact with the world. And he's controlling this through signals, electrical signals recorded at the surface of his body. So this isn't going right into his brain or his nervous system. He's really looking at using the periphery of his body to control these robotic devices. It's not even so much that people just strap devices onto their body. This is another example of something called osseointegration, something that we're hoping going to translate to Edmonton rather shortly. But this robotic limb is actually affixed directly into the bone structure of this individual. So he's got a socket in the residual limb, and there are metal pieces that essentially click lock into that socket. So this prosthesis is now a removable but well affixed, a firmly mechanically connected part of his body. He has a strong mechanical connection, and researchers like Max Ors-Catalan and others are even looking at making this electromechanical, running wires through that socket into the nerves and muscles of the body to both sense and record from the peripheral nervous system. This is also used in the lower limb, and heck, this was used in dental implants long before it was used in arms. Keeping going. You might want to use a robot arm in place of the body that was lost due to something like lower limb paralysis. Other researchers, like those down at Cleveland FES, are looking at just saying, well, if we can record from the brain, we can actually take those signals and just pipe them back into the body by implanting wires under the skin and into the muscles, be able to generate a new whole synthetic electrical nervous system to overlay the biological nervous system that's no longer functioning or no longer being able to be controlled by the person. In this case, it can stimulate muscles so that someone could even begin to control their own body using impulses from their brain without going by way of their spinal cord, which is at present still irrevocably damaged and unable to be restored. We're doing some cool stuff up here, and again, this is my rapid fire, keep you awake, and then maybe you just go to sleep for the rest of my talk, part of the talk. We're doing something really cool up here in Edmonton as well. It started down in Chicago, but we do it here as well as a World League Center, and that's actually rewiring the biological nervous system. So not just taking a new electrical nervous system, but working, this is work by my colleague Jacqueline Hebert and Ming Chan and some of our plastic surgeons, looking at being able to actually take the nerves that would have gone to a missing part of the body and restring them, rewire them like you might rewire the wires in the walls of a house, such that a person could begin to interact with their world in different ways, that they could begin to provide and receive more signals from a robotic device attached to their body. And I mean, I said wires, but we don't even need wires. So there's a lot of technology now that is looking at implanting small wireless mesh network devices within the peripheral parts of the body, within the brain itself. There's a number of initiatives right now looking at deploying small grains of rice-sized devices within the brain such that they can communicate, they can record, they can stimulate. And similarly, this is an upper limb implantable device which has proved to be long-term stable in humans. People are controlling brain-machine interfaces like wheelchairs and working together with machines to be able to navigate environments, to use their wheelchairs alongside machine intelligence to interact with the world in ways they couldn't. This is not just research. People are actually wearing these things in the real world, in the wild, as you could say. There are clinical deployments of advanced technology like that that are being prescribed all across the world right now. They aren't as advanced as some of the examples I showed you, but there are people actually using this technology. It's not just something that lives within a research lab. There are devices you can buy from big box stores, although one of them I think you still can't buy right now, but that doesn't, for a couple $100, you can actually buy devices to interface with your own muscles, with your own biosignals, with the signals coming from your brain through your skull. You don't have to drill. We took away all the bone drills in the lab. Craig, are you here? No? Yeah, we took away the bone drills in the lab for exactly that reason. And we're able to 3D print our own environments. I like this is one of the press photos, but I really like it because it shows one of our participants with an amputation working with our team and also with our 3D printed environments, our 3D printed technologies. That's the bent arm that some of you may have saw when you went up and toured Amii during the career crawl. Okay, cool. So why did I show you all these cool examples, besides the fact that I think that they're really exciting, is because this, in my mind, represents the bleeding edge of ambitious research for the human race as a species. And in fact, all of these examples, in one way or another, though I didn't actually say it, all involve machine learning or machine intelligence, advanced computing technologies that form the glue between the person and the technology that is augmenting or extending their abilities. This is the picture I always like to show. I probably should revise my slides because it's a bit dated, but you can imagine that the human body is an amazing generator of signals, both flowing in and flowing out. And the assistive machines that we are now connecting people to also have an amazing repertoire of signals that transfer both from these devices and to the devices themselves. The pitch here, and I think the compelling argument, and the thing that I showed you in all those other examples, is that in fact machine intelligence is the glue that we can imagine connecting all of those signals flowing to and from the human and all those signals flowing to and from the assistive device. Okay, that's a lot of signals, especially if you imagine detailed brain recording or nervous system recording. And so I guess this is the bit where I'd like to step into how we start to pursue ambitious research in places where it might be challenging, is that, I don't know about you all, but I'm not sure I would like to do trial and error learning on the wires going directly into the human brain. Probably not. So by analogy, if that doesn't sound too real, I shave with a straight razor, so in the mornings I'm like, wow, okay, I'm gonna actually take off these loose hairs with a lethally sharp piece of steel. I would also not do trial and error learning on how I shave with a straight razor. Oh, what's this angle look like? What's this angle look like? There's a path towards learning how to interact in such dangerous or safety-sensitive situations that allows us to move forward with research without storming the castle by the front gates, without doing something that might be inherently very dangerous or time-consuming, or just really sets you up for a 10-year window with no actual research papers, and then you don't get tenure, and then all these bad things happen. So, how do we get around this? And it brings me to the whole point of this talk, because I think really I'll go back to that point I mentioned earlier, that the whole point of this talk is to highlight prediction learning. And now I can leave because I'm done. Look, it's in pink. We're good. Oh, sorry. Highlight prediction learning as a foundation for more advanced control solutions. Highlight prediction learning, or you pursuing prediction learning and machines pursuing prediction learning as one way to attack very ambitious problems. So we're going to jump into that. Okay, I think everybody knows about predictions, right? You spent most of the week on some level, I think, probably talking about predictions, and probably last week too, and you maybe talked about them in the evening. So I just want to have a refresher. Again, I promise no math, but there's several kinds of predictions that you might think about, or several ways to slice the field of prediction. And one is the one that I think is almost the most common form that we think about, which is a momentary form of prediction. It's like a classification decision. If you want to see references for how this is done in, say, peripheral human-machine interfaces, there's this awesome, Sylvester Massaro and colleagues have this awesome review back in 2010 that's still relevant today. For those of you that actually paid attention for the rest of this week, you'll also probably be familiar with temporally extended prediction learning. Learning about patterns that will evolve into the future. The expected return is one such thing that you might hope to learn. And the Horde paper, I know some of this was mentioned earlier, the idea that you might make temporally extended predictions about signals that aren't reward. Wow, crazy, amazing. Rich said that in his 1988 paper. Anyway, you can make predictions about temporally extended signals that are not reward. So momentary predictions, temporally extended predictions. And as I think everybody here knows as well, you can acquire and update these kind of predictions in batches, or you could do it in real time while the system is actually learning or interacting with the world. Cool. And this gets back to my earlier comment about prediction, and that, in fact, there's a wealth of literature from the biological side of things that says something very profound, that prediction precedes control. And this is an image from Calvin and Hobbes that was stolen by Wolpert and Flanagan, which was then stolen by me from their paper from Calvin and Hobbes. Anyway, this is a picture which really nicely illustrates this, but I've also listed a series of papers here which I almost consider required reading for all the folks working with me. I recommend them to everyone, but it's all about how the brain uses predictions. The idea that our brains, our biological brains and brains of other animals acquire predictions, the ability to predict the future of data streams, before they acquire control behavior, the ability to actually manipulate the world. I have a toddler at home, he does a lot of this on a regular basis. And that when we look at motor learning, when we look at learning complex, ambitious skills like me shaving this morning with a straight razor, is that there is a lot of prediction learning that precedes the control. And our cerebellum does a ton of it. If you want to see a close analogy between, say, the Horde architecture that was put forward in 2011 and a biological part of some system, you can look at the cerebellum as a massively parallel system, which makes many, many, many predictions. Joseph Modell and colleagues would call this nexting. There's also, just as, by way of a side note, there's also some very interesting literature by folks. This is one example published in Science, where it shows that, in fact, the whole feeling that we're doing something, the feeling that I'm moving my arm or maybe going to go kick Cam, is in fact the prediction of the motor outcomes. That my feeling of ownership over performing an action isn't even, in fact, that I'm doing it. It's not the sensory feedback. It's my predictions about motor outcomes that are then eventually rectified with the sensory feedback that trickles in from my very slow biological parts. So, prediction precedes control in motor learning. There's a paper titled that. You might want to read it. It's really cool. I like it. But that's where we're going to go, because I'm going to sort of ground this now in my diagram, and this is just mine. You can all disagree. You can have your own perspectives on what the hallmarks of intelligence are. But for the purpose of discussions like this, I really like to try to settle down into these three elements: data, decisions, and goals. Okay? And that really, data, goals, and decisions are hallmarks of intelligent systems that are both artificial or synthetic and biological ones like us humans. And what drives through this, what really allows that data to be turned into the achievement of goals by the choice of means, is in fact a elegant interplay between perception, more than just sensation, but real perception, representation of the information in a data stream, the transformation of that into what might be considered prediction or knowledge or forecasts, some understanding of the patterns that goes beyond raw perception, and right through to action, the ability to put bits on wires, to have something that might, hopefully, change the world. There's an example of how this changed together. I'm not going to dwell on this, but it's some work that I did with Johannes Gunther, who's now a postdoc here at Amii, and where you can start to see this was a laser welding system. Don't worry about the details, although it is applied robots, et cetera, et cetera. But really how we were thinking about streams of data going into a deep, this is like even before like deep nets and combining with RO was really cool. But putting essentially sensory motor data into a deep neural network representation learner, which then fed out into actor-critic control processes, into control learning processes, and out into prediction learning, temporal difference prediction learning processes, which then came together to inform how a robot arm with a laser on the end cut and smashed through hot metal until it became one piece of hot metal. Cool. So, Nadia's just chuckling. She's like, that's the best summary of research ever, right? I know, eh? Cool. So we're doing pretty well on time because I speak really quickly. So I'm going to dive into the next piece. But before I do, like any one or two quick questions. Anyone have anything that they're like, oh man, that's totally wrong, or wow, you really mischaracterized that? You're all really tired. I get it. That's cool. Okay, awesome. I just want to check. But if you do have something that's burning on your mind, just like raise your hand, jump, scream, or something. But otherwise, I won't make you interact because it's really late in the conference. Okay. I'm going to ground all of the rest of this then. So I've tried to pitch you, again, the idea that there are ways you can go through very ambitious research spaces like human-machine interaction for intelligence amplification. And it's a gentle way that starts in prediction. So now I'm going to walk you through really a case study in this, which is over the last 10 years here at the University of Alberta with our international collaborators, we've been trying to really solve the intelligence amplification problem for humans interacting with their upper limb prosthetic devices, robot arms attached to their upper body. And so I'm going to use that as a case study, again, partly because it's the thing I know best and probably the only thing I'm qualified to talk about. So I'm going to talk to you about this. And it's all about how humans become to embody a robotic body part as part of their own body, and why that's really, really tricky. If you want all of the gritty details, Rich and I spent about 7 years with a bunch of our students writing a paper called Communicative Capital for Prosthetic Agents. It's up on archive. It's about 33 pages. So it's a longer read, but if you want all the nitty-gritty details of the core elements of what I'll say next, you can dive into that particular manuscript. Otherwise, I will give you the Coles Notes version, and you can leave that for a future life. Okay. Here's one of our robots that's sitting in the lab right now, although it's sitting in a different part of our lab. But I just want to highlight that robots are obviously complex systems, but that it's not that robots themselves can't do all sorts of incredible things right now. This is just one pre-recorded pattern of motion, and you can see that it's performing what amounts to biologically comparable movements. It's a little jerky, it's not doing it perfectly, but I mean, you can't really argue that, oh wow, this arm can't actually do to a first approximation, many of the motions that you might expect from a biological human arm. It'll do little finger wiggle things, and it can pinch things, and like, it almost has lumbricals and interossei, like all these different muscle groups are represented by the actuators of a system like this. It's got over 100 different sensors, it's got 17 to 22, depending on the version, controllable degrees of freedom. Like, it's a complicated robot system. And then you put it into an environment where it's like, hey Gotham, this is Gotham Vossen, my ex-MSc student, he's now at Kindred, and like, Gotham was shaking hands with his robot is an awesome example of how we try to actually do very simple things with our robots, and it immediately becomes a little bit harder. And let's just go from there to actually one of our participants with an amputation. This is a gentleman who comes by and works with us regularly, and he is using one of our 3D printed arms, but using conventional control, the way that you might see someone controlling a robot arm as they were fitted with a device in the clinic. And what I hope you take away from this is that, in fact, his control of this particular device is really slow and painful. Like, you'd expect anyone with both of their biological upper limbs to be able to grab a ball and transfer it to a cup very, very quickly and smoothly and efficiently. And here this gentleman is actually having to navigate his way through a control interface, to select different modes and functions, and be able to select the correct one at the correct time, such that he can perform this, what amounts to a simple manipulation task. But it's really not that simple, because we do this every day. When we're moving around, moving the parts of our body, we coordinate a massive number of actuators. Think of all those little motor units and all these little bits of information that are being turned on and off through our entire nervous system. And now we're asking someone who's, say, lost their natural interface to this kind of device to be able to perform a comparable motor activity. And here he's going to be like, I'm going to eat the ball. It's going to be awesome. Eat the ball. Oh, wow. Eat the ball. Yeah. All right. So, and then it drops. And like, oh, no, now what happens? And did you catch that? See what happened? The ball dropped, and he used his biological limb to try and grab the ball. So right away, I'm using all of this as a motivation to say that this is a really hard problem. So I'm going to go in the Wayback Machine back to 2009, where we had the starry-eyed wonder of saying, oh, yeah, this is a really hard control problem. But you know what, we can just tackle this head on. Let's actually try to, we're going to do control learning. It's going to be awesome. We're going to use actor-critic algorithms. Those are trendy. And we're going to try to actually get some traction into allowing the person and that device to really rapidly co-adapt. It turns out it actually worked. We have a really cool paper. I like this paper. Other people seem to like it too, where we actually looked at how you could just train a robotic system to follow your motor intent using human-delivered reward. This is back in 2011, and we're like, oh yeah, you can just train it with pluses and minuses, and it can learn control policies. But even though the work could be considered a success, and I think it was really interesting work, is that it opened up far more problems than it closed. And in fact, it showed, just really for us anyway, how hard it was to try to tackle the control learning problem in a setting where you have a human and machine interacting, and the stream of information flowing between them was getting only more detailed every year that we tried to solve the problem. So from my perspective, this is where I took us and our team is like, well, you know what, okay, if we can't, and this gets back to the main message of the talk, if we can't solve the control problem head on, well, let's just see, could our system even see a way out of this problem? Could our system even begin to see the patterns it needs to solve that harder control problem? Can it just predict the future of the data stream it's interacting with? Can a robotic limb attached to the human body predict things about its own motion, predict things about how its human is going to respond in a given situation, predict situations and environments to a degree that it could actually do something useful when it's placed in full control with the human body? We're like, we're going to dip down there for a year. We're going to figure this out for ourselves and for the system we're interacting with. And then we're going right back to control learning. And control learning, that'll be so old hat by then. We're going to do planning and meta learning and a bunch of other really cool stuff that clearly is what we want to do. That's where everyone's publishing papers. That's going to be really hot. And then it turns out that's not what we did. We realized that even the prediction problem, to build a system such that it could actually intimately capture the regularities of the data stream, its interactions with a person, that was a very hard problem. We started studying it even more deeply, and I'll walk you through examples of how we've done that. And it took us down even farther, to the point that, we realized that it was even studying the representations, the way that the system at a very base level, like an artificial limb, begins to structure the data in its environment, was also something that we need to fundamentally consider, both to design better systems and so that we, as experimenters, understood the right problems to solve, so that when we did apply ourselves to this astronomically hard space, this astronomically large space, that we could come up with the right solutions. And the way we did this, and so this is starting with the prediction, like example 0, is the case of just can a system, like an artificial limb attached to the body, can it begin to actually make predictions in real time? This is something called nexting. This is really what I'll be referring to. The idea that you might ask a system to learn through data, through its own interactions, what's going to happen next. Joseph, Adam, and Rich wrote a really cool paper about this that was published in a workshop and also then published in the journal Adaptive Behavior. And so I encourage you, if you're curious about this and some of the talk of prediction learning and temporal difference learning earlier in the week got you excited about it, that this is a really nice paper, but it's all about how systems can learn what's going to happen next with respect to their own data streams. The idea here, and this is how we first tackled it, is that let's just put a person, again, I'm giving you a case study. Let's put a person and a robot. In this case, we had an individual who had undergone one of those nerve rewiring surgeries I mentioned to you. So we have someone who has a reasonable number of connections to and from their biological body, and a robot arm with a reasonable number of actuators. Can we put them together into a single unit and then put a learning machine on top of that, essentially just watching the flow of information, that pipeline of sensory motor data, very detailed sensory motor data, flowing between the person, the control system, and the robot itself? Can we find some way to approximate, to make these signals take a form that is in fact learnable by a machine learner in real time with reasonable computational constraints? Not sending it up to a server in a cloud, but actually something that might run on an embedded microcontroller within the device. And then can we have the system begin to make all sorts of forecasts, predictions about what will happen next in terms of everything from the motion of the robotic arm, the way its joints are moving through space, the signals coming from the human body, like the electrical impulses coming from the muscles of the human body, and even the states and the changes in the control system itself. Can we build a system? This is like probably a really boring question for most of the folks thinking like, no, I'm gonna make stuff like, juggle or like ride a unicycle. This is a really, maybe what seems like a very humble or boring problem by comparison. But I encourage you to think that for us, when we were tackling this in a space that we knew nothing about, that this was a very hard problem on itself. I'm really proud of this paper. This is what I consider to be like my postdoctoral thesis. But it was a paper just about making predictions about a data stream. We've since gone farther. This is like after that we decided to see if we could even scale this nexting approach. We made maybe a dozen predictions in that previous work. We showed that a system could on its own, from data, with no other human interaction, begin to predict things about its own motion, its human user. Craig Schurst and I and some of the others in the lab then dove in and said, well, can we do something even a little bit more ambitious, but still in the flavor of nexting, which is that can we take a system like this one, the MPL here, the fancier robot arm, and just take the raw data packets coming from it. Let's do nothing else. Let's not parse it. Let's not even turn these data packets into floats and headers. Let's take the raw bits flowing over. In this case, it was a UDP broadcast connection. And can we see if a system can start to build up predictions or forecasts without any kind of knowledge or labeling about what these bits are, about all those different bits? And in this case, we were making about 18,000 predictions in real time, a very large hierarchical architecture of generalized value functions for those that know that particular space. And we had a little cool demo. I like this demo. Well, you see here, the left box there is like the predictions being made about the bits in the system. The middle box is a measure of surprise. And so when I come up here and mess with the robot, I shake it, you can see all those lights flare up. The system is able to make predictions, but using Adam White's UDE surprise measure, we can actually see that the system can detect when it's wrong about its predictions. And the next piece here, just from this is a really cute little demo. Like literally took me about, I don't know, a day and a half, and mostly was trying to figure out how to decode UDP packets. We could also show that we can make predictions about those surprise bits. So the system could learn not only to predict the future of its bit stream, it could learn to detect when its predictions about that bit stream were wrong, and then be able to build up predictions about when it might be wrong in the future. The example I always like to use is like if I'm sitting at home on my couch watching Netflix, I don't expect to be surprised. But if I'm walking down a dark alley in a city I don't know, I predict that my predictions might be wrong. And so this little simple demo showed something along those lines. And so what was really nice is that Johannes Gunther, along with Alex Carney and Rory Dawson and Craig Schurston and Nadia as well, I'll put up that reference in a second, decided to make that experiment a bit more formal. And so this is a very recent paper, came out last year at the AAAI Fall Symposium, but looked at building one example of a network of prediction learners like the one I just talked about, and show that a system can in fact begin to, slide break, there we go, learn predictions, and we can study the way that learn predictions about all the bits as we repeatedly perturb the system. So again, now let's just dwell on how probably vanilla and boring this kind of experiment is. We had a robot arm sitting there doing nothing, and then we had someone, I think it was Rory, go in and for 20 minutes go push, push. Okay, yeah, and like that happened 21 times over the course of like a 20-minute experiment, and the whole point was to then study the way that the system was able to build up individualized predictions about each of the bits in that bit stream, study the way that it started to learn. This plot up here is actually showing the system detection of its surprise when it was repeatedly perturbed, and also look at its ability to forecast, reliably forecast, the future perturbations in this data stream. Again, this is really all we're doing is just making lots of predictions and studying the behavior of those prediction learners en masse. And what was really cool, this is another paper that we did shortly afterwards, and there's a journal-length paper going in soon, I think. Nadia's nodding, this is awesome. This work with Johannes and Alex and Nadia and Rory, looking at doing massively parallel step-size adaptation on that same data stream, on a very similar data stream, and showing that the way we can actually study from a meta-learning perspective that the way that the system adapts to make those predictions, the way that it might say tune its step sizes, can actually allow a system to perceive other things about its operation, whether its sensors are broken or stuck, and to be able to essentially self-tune the prediction of this large population of learners. So this is cool, and I'd like to point out that it's all predictions. So I'm like, if I asked for a question right now, someone would pop their hand up and be like, okay, that's awesome. Yeah, you made lots of predictions. We get this from reviewers too. We get lots of predictions. What are you going to do with the predictions? Like, what do you do with them? What are they good for? What are they useful for? I think how many reviews have we got to say, well, you make lots of predictions. What are they good for? Horde paper, 2011. What is that good for? You guys clearly know nothing about reinforcement learning. Yep, anyway, so the answer is, and this is going to get to the whole point of this talk, which is that I hope to say the phrase Pavlovian control enough that you probably remember it next week. All right? And by Pavlovian control, I really mean, and Joseph's not around, is he? That's too bad. He could give this part. Pavlovian control really involves something very, very straightforward. It's not full control learning. Pavlovian control, and this is nicely, again, unpacked from the biological literature into the computational literature by Joseph and Rich, is a fixed mapping between learned predictions and fixed control actions. The example, like if you see someone like Jim Kehoe give a talk about rabbit eye blink behavior, it's like a rabbit learns to predict a puff of air, and the minute that it predicts a puff of air, it closes its eyelid. It can't control the closing of its eyelid. The minute that that prediction goes above threshold, the rabbit has to act. It will close its eye. But it learns the prediction about the impending, say, puff of air or a twig as it's running through the bush. So it's a mapping, a fixed mapping between learned predictions and control actions. And so when people say, well, you made all these predictions, and this is a really hard space of research, what are you going to do next? The answer that I give is that, well, we're going to first look at how we can use some of those predictions, handpicked, admittedly handpicked, to begin to solve aspects of that hard, grand research problem. And with the time I have available, I think I can tell you about 3 examples. The first example is one of my favorites. It's like what I consider to be like the transgenic mouse of my entire research program, which is a very simple machine learning system that we have developed over a long period of time that helps to modulate the interactions between a person and a machine, and that now we can poke and prod and study and actually try to understand the relationships. Adaptive switching is at its heart a system wherein learned predictions change something about the interface between a person, and in this case, an adaptive upper limb system. This is the work of Ann Edwards. Ann has a pretty spectacular master's thesis on adaptive switching and autonomous switching that she carried out a number of really great studies with people without amputations and people with amputations to study how we might start to improve the interface for someone who, with a limited control channel, maybe just a single sensor on their body or a pair of sensors on their body, might control a system that has many, many different actuators, wrists, elbows, individual fingers. How someone might be able to gate their control or switch their control between a complex control system and, with the help of a simple prediction learner, begin to actually optimize that so that they have to act less, think less, and do more. That's the heart of adaptive switching. So like one of the examples, this is a video from our lab with one of our subjects with amputation who came in. And he was looking at a really simple task. He's switching between modes and functions with his right arm. You can see him flicking his arm. He's moving this robot arm back and forth to do a really, really simple task. On one side of the space, he's going to try and wave the wrist. On the other, he's going to try and, I think, open and close the hand, if I remember correctly. Yeah, there we go. And so to do that task, he has to also switch his voluntary control between the elbow actuator, between the wrist rotator, the wrist flexor, like all of these different joints or functions or modes of the system. He has to manually gate his attention. And as he interacts with the system, as the system begins to predict what he wants and when he wants it, the system begins to optimize that switching list for him. It begins to optimize the order with which things are presented such that he gets what he wants when he wants it. Now, this should also surprise nobody. What does your phone do? What does your laptop do? It sort of tracks what you're doing. It makes predictions about the next app you're going to use, and it usually shows you that one first. Like, I don't know, I've got an iPhone. I swipe to the first, like that little control screen of my iPhone. It's like, hey, you're probably playing Pokemon Go everywhere. Anyway, it's got a really good predictive model of what I might be doing at any given time. And that's exactly what we see here. So I said it's all about taking a small cherry-picked set of predictions and then doing something maybe even only moderately clever with them. In this case, if you think of those like colored blocks there, I had to show you wiggly lines to be a good scientist. So, I mean, here's your wiggly lines. If you look at the colored blocks, all we had this system doing was, as someone was interacting with that system, like you saw the gentleman interacting with the system, have the system begin to build up predictions about when the person might be moving their wrist or their shoulder or their elbow or the hand of that robot arm. And then doing something really, really simple. Like if you look at even that, there's like a little green arrow there. At the point that the person decides they're going to switch to another motor function, just look at the magnitude of those predictions. This is not fancy. It's not clever. It's just saying, hey, you can make predictions about what someone's going to use. Let's just take the best or the highest prediction that we've learned to date and give that option to them first. And then the thing that's next most likely to be used, we'll give that to them second. Turns out that doing something so simple, like this is just building and learning predictions in real time. This wasn't training and testing. This wasn't, oh, hey, we're going to train this on 50 users. This was, we drop someone in with a robot, and 5 minutes later, it's got good enough predictions that it can actually start to optimize their switching list. Any of you came to RLDM? Anyone come to RLDM? Oh, good. Okay, a handful of you. We had a demo of this there, and you could have like interacted with it, and with a couple minutes, this isn't like a billion steps of training data. Within a couple of minutes, it would already be able to learn something about the patterns of your motion and be able to optimize the control interface for you. So this is a way of going from just understanding how a system might make predictions about a specific application, and then using some of those predictions in a clever way to start to tackle that core problem, the interaction between human and device. It also turns out that if you do this really, if you actually understand the space well enough, we spent a lot of time, Anne spent her whole master's on this, you can also, if you know when someone wants something and what they want, by putting those two things together, when a system's really certain, it can just start to do some of the things for the person. And so we showed that a system could learn and unlearn. This is Jaden Travnik, who's now out in Montreal, another one of the students in the lab at the time. Looked that the system could actually start to take over some of the voluntary switching of attention in cases where it was like really, really clear that the person was going to do one thing or another thing, and that it could actually streamline the number of manual interactions that a person had with the system, but at the same time did not remove the human's ability to do whatever they want. So the human could always do the thing they want, but the system began to take over some of the actions that might have been more complex or more repetitive, offloading some of that intelligence. Oh, now we're at funders. Okay. Oh, yes, please. Yeah, it's really cool. I like that you brought up this question because the natural thing that we might think is, well, I mean, this is the RL week, we're probably using reward. And what's cool is that we didn't, in all the examples I just showed you, there was no reward. So that was a really cool thing. It was a temporal difference learner, but the system was building up predictions about, essentially the question being asked was, by the system, if I were to switch for the person right now, would they use the thing I suggested? And so what's neat about this is that it's like an in-channel, it's a kind of prediction that will correct itself just by watching what the person does. So I mean, it can start to build up the prediction watching how a person switches between the different modes and functions. And then when the system begins to switch for the person, after it reaches, say, a certain threshold, that's the really simplified thing that we did, if it were to switch for the person and they were to switch back to something else, then its answer to the question, would the person use the thing I switched to, would be, no, they wouldn't. And so it'll decrease the prediction. So it's Pavlovian control in the sense that there's a hardwired mapping from the prediction to, in this case, the switching behavior of the system. And just by the user's activity, it will increase or decrease those predictions. I think Mike Bowling said he was on the thesis defense at the time. I think he even said, well, you could do this with reward too. And the answer is yeah, I think we could. But this was a very straightforward way that we could obtain the behavior we wanted and truly understand the process, yet without pulling in the complexity of full control learning, which means it could be learned really quickly. Does that answer your question? Awesome. Okay, on to motor synergies. Cool. All right, so if anyone, Nadia was convincing me that I should have someone throw stuff at me. Normally if I was doing this, we'd have a big interactive session. I'd have you out in the hallways with worksheets, but it's Friday on the last day, so we're skipping that. But if someone were to like throw some, I'm going to step back actually, I see only like hard objects. If someone were to throw something at me, how would I probably catch it? I'd go maybe like this, or like this, or like this, or like this. But either way, I'm moving many of my joints together. I'm moving my body in a coordinated fashion. And this is something, again, another facet of this large control problem of humans controlling a robot body part, is that people really can't control simultaneously, smoothly, and in a coordinated fashion all of those pieces of their body. This goes back to prediction precedes control. I have to forecast where my body needs to be at any given time and unfold my joints in just the right order to be able to perform the action I want to perform. And so the next thing we looked at, again, another example of Pavlovian control, was, again, same thing. Same thing we were doing in all the rest of these studies is building up predictions about the motion of a system in real time, and then just mapping the predictions to actions. Before we map the predictions to changes in an interface, in this particular example, there's a series of examples, we looked at mapping those predictions to actual actions. And this is, I yanked this figure from Craig Shurston's paper in his master's thesis on intelligent robots. But the idea is really simple, that if you have to coordinate many, many joints and functions, and a person is only able to control one of them at any given time, well, if the system's good at making predictions about the real-time behavior, nexting about the future of the stream of interaction, and then the system's nexting predictions should be able to fill in the gaps for you. It should be able to say, if I'm trying to bend my elbow, it should be able to predict where the wrist should be and where the hand should be at any given time. And then when I finally start controlling the wrist or the hand, maybe it should start predicting where my shoulder is going to be and filling in the gaps. So it turns out that this actually works. And I'm going to, maybe I'll show, I don't know if the video played. No, it didn't. I'm going to go back. Oh, wow, the video was actually already playing. And we looked, nope. Hooray! Okay, great. So we actually looked at a very simple problem, which was controlling the wrist of a robot so that, and Osmar, this is the robot I was mentioning with the broken wrist. It's from that study on the bottom there. But turns out trial and error control learning actually also destroys robots. But this didn't. And the idea for this particular piece I'm showing you here is that you could start to make predictions based on watching someone control a robot of, say, where a wrist joint needed to be to achieve different poses. And then, while the person is controlling that robot, have the wrist be controlled by the learned predictions. A simple temporal difference learned prediction about a single joint, in this case the wrist, that output, that prediction, could be fed in as the control action that was in control of that joint while the person wasn't using it. Craig Shurston also looked at controlling, while navigating a robot arm through a maze, looked at controlling other joints of a system while the person was controlling, say, the horizontal or the vertical axis. The prediction, the temporal difference learned prediction of the other joint could control the other part of that actuation problem. Again, this isn't fancy. This is exactly the answer to the question, well, if you make lots of predictions, what might you do with them? And this is solving another piece of that larger problem. The last example before I start to wrap up and I'd like to give us time for questions, so I'm going to try to power through a little bit to the end. The last example is, in fact, one about communication. So far to date, we've talked about how we might interpret some signals from the human body, their control intent, their switching behavior, the signals from their muscles, and map that into control actions for a robot. This is a very natural thing to think about. This is what most people are thinking about. Most of the commercial machine learning approaches now to controlling robot arms are looking at learning and mapping control intent from the human body, say the signals of muscles on the residual limb, to the actuators of the robot. This work is exactly the opposite. In fact, we started to look at how a system might begin to give feedback back to the person. The reason why we think this is really cool, especially here in Alberta, is that I told you about those fancy rewiring signals, the rewiring of the nerves in the human body for someone who's lost their limb. Because of that, the people who've undergone this procedure, if you were to, like, say, stroke them on their arm here, they would feel it in the hand they no longer have. Rewiring the sensory nerves that would have gone to the amputated limb, such that now physical embodied parts of the human frame can actually be a direct connection to the part of the brain that was originally responsible for feeling the brush in the back of a hand or the tap on the front of a finger. We now had a window back into the way that a human perceives the world through the hand that they no longer have. Our robot devices, by way of some very clever mechanical innovation by other parts of the team, the robot could begin to actually interact with the new rewired skin, such that the person could begin to feel what their robot arm was feeling to a first approximation. All of this was done in a hard-coded or a hand-mapped way. And so one of the things that we started looking at was, well, in the same way that we can start to use predictions to improve and modulate the way the person controls a device, can we use it to instead feel something from the robot? And so one study I like to mention, I have two examples of Pavlovian control for communication and feedback. One of them is done by Adam Parker over a series of experiments. This is the most recent paper just published at ICOR. And what Adam did was essentially put someone in control of a single degree of freedom arm, like a single arm that just wiggled back and forth, put that arm in a box, blindfolded someone, put on noise-canceling headphones, and then said, try to touch the box, but don't touch it too hard. Okay, this is kind of hard if you don't feel anything about the system. So if I put any of you in that situation, you'd smack into the box, you'd probably blow out some of the robotic joints. So what Adam did is then gave two different control conditions. One was that the person could feel the immediate impact or contact with the box by way of a vibrating motor that just buzzed on their skin. And another was that he had a single prediction learner, a single generalized value function, which learned to forecast the future load that the motor might experience, how much current it's going to draw. This should be a proxy for impact. And instead of giving the direct feedback signal to the person, gave the person vibratory feedback based on the system's predictions about future impact. And not surprisingly, and this is a really cool finding, was that the person who used the predictive feedback, the person who had feedback that told them something about what was going to happen in the future, much like our brains are doing all the time, was able to burn a lot less juice. They used a lot less current, and they were able to get closer to the contact with the wall without over-juicing into the wall itself. The other example, this is some newer work in collaboration with both our DeepMind team here and the University of Alberta, was looking at in human virtual reality foraging environments, being able to signal people using, again, learned predictions, temporally extended generalized value function predictions to signal people as they interacted with a virtual world so that they might be able to perform better in this case, a virtual foraging task. And that's on archive too if you want to have a look at it. But I'd like to move on. Okay, sorry. I first should say, don't get me wrong. We also did control learning. Gautam Vasan had an awesome thesis on learning from demonstration, where he taught a robotic limb to mirror the biological limb. So if someone has one arm that is an amputated arm and the other that is a biological limb, makes sense. You could just do some mirrored learning from demonstration training. There's actor-critic control learning. In that study I showed you earlier, where I told Osmar that we broke the robot, we also looked at using generalized value functions at predictions learned in real time as input, as the only input to, say, a policy gradient learner, as input to a more complex control learning process. Because predictions can adapt really quickly, 5 or 10 minutes, and they might be able to adapt to a new situation. But the control learner, through trial and error, takes much, much longer. So just even putting in real-time learned predictions as predictive representations of state also has great utility. So we did a lot of other stuff too. That's not really the point of the talk, so I'm going to gloss those over, but you can go track down the references if you like. Because I'd like to get back to this. This is the picture that I painted for you at the very beginning. This is the big idea that I pitched, was that the human body, and this is why it's an ambitious problem, has many, many signals flowing into it and away from it. Our assistive machines, as they get more complex, Osmar is holding his iPhone right now. Many of you are probably checking your Facebook or Twitters or something like that, or just having a nap with your screen in front of your face. Either way, you're interacting through a detailed stream of experience with assistive technologies that might be both physically and digitally instantiated. So this is a complex setting. And what I really talked about was trying to find a way to create that block in the middle without having to create the whole block in the middle. How can we start to make some paths through that space that help us understand how we might someday, ambitiously, begin to fill that entire block, or have a system for itself, create that interface? I like to call it universal glue. This is when people are like, what are you going to do with your next 20 years of your career? I'm like, I'm building universal glue. And they're like, what's that? I'm like, it's that blue stuff. But that really is what I see as my long-term career objective, is to figure that piece out. And I don't think I can engineer it myself, but I think that by doing these small, incremental, additive steps, is that we'll start to be able to carve out the landscape that will someday be this universal glue thing that I'm really excited about. And it's I see that this is another, I'll show you one more human-machine interface video to end here. This is by one of the Berkeley spin-offs. But we're seeing that devices now are being used as part of our daily life on a regular basis. These are gentlemen with exoskeletons, robots that are worn on top of their body. I didn't show you exosuits, so I had to show you now. But people are now having more and more regular, more consistent, and more detailed interactions with the technology that surrounds us. In this case, literally surrounds us. It's not just limited to someone connecting to an artificial limb or their self-driving cars or any of the other things that we might interact with. It's really this picture. And so I'm going to sort of use this as my punchline picture, which is that it's not just a person connecting to an assistive device. It's that we are using technology, and we've always used our technology to augment our abilities. We've always used our technology to extend our ability to perceive the world around us, to act upon that world, and to put it all together, to cognate, to think about the complexity of the world. Machine learning is the most powerful tool. Machine intelligence is the most powerful tool that we can probably create as a species. It forms that glue. Everything we're doing is forming the interface between our mind and that complex, blooming, buzzing confusion around us. This is, in fact, one of the core things that we do. And so I encourage you to think of this as an ambitious project, and that even when we make small steps into certain domains, like me trying to figure out how to have someone embody a prosthetic device attached to their body, this is the grand problem that we are thinking about. Which really, as we move into this, I'd like to get this back to our spinning wheel. What I tried to communicate today, and you don't have to believe me, you don't have to agree with me, is that there are natural steps, much like the way that we can see the evolution of automated weaving, is that there are direct paths towards solving goals. Those are great. We should do those. We should try for that approach. But that there's also incremental, additive. There are storming the castle not by the front gate approaches that will allow us to move towards the solution to very, very ambitious problems like the ones that we looked at. And I mean, this is sort of a plug for any of the constructivist AGI folks in the audience, is that, I mean, I don't actually believe, I don't believe that we can build that full block in the middle ourselves. I believe that as much as I said that we start having an approach wherein that we as designers and we as agents and our agents begin to build up understanding, representations, and predictions about the world that surrounds them, about their data stream, that we should hope that the systems themselves begin to take on some of the structuring of those predictions, of those representations, so that we're not doing all the heavy lifting. I think that this is actually the end run on this, but it's one that many people in this room are contributing to. Which gets me back to the whole point of this talk, which really was to just keep you awake with cool videos long enough so you get to see Rich's talk. Okay, and you're all still breathing. This is great. So I think I actually achieved it. Maybe it wasn't it. Maybe the whole point of this talk was actually to convince you that, in fact, IA, intelligence amplification, is not just a grand challenge, but the grand challenge for everything that we do in deep learning or reinforcement learning. Maybe that was it. It could also be, and this is probably the most likely case, that I was really just hoping that you sort of, grok that prediction and control design pattern that we talked about. That if you really want to understand a system, if you want to understand how you might solve an ambitious problem, like do what Rich has always advocated we do, which is like be the algorithm, jump inside its head, see if it can actually predict the future of its data stream. If it can't predict it, it's very unlikely it's going to be able to control it. So if you have a choice, and if you're building out your own research problems, if you want to do that in a way that is incremental, that allows you to plant down research milestones, and milestones in your own understanding of a problem space, I would encourage you that really you can start with prediction. It may sound humble, it may not impress people, you may not get papers into iClear and NeurIPS if you do this, but you will be able to carve out understanding as to the space of the learning problem that you were interacting with. You'll be able to make traction, and you'll be able to scale towards those ambitious goals probably a lot faster than if you tackled the problems head on. So please consider this to be one possible design pattern that you can use in your very diverse careers as you move forward. That's the main thing I hope that you'll get from today. So with that, thanks very much, and I think we have like 16 minutes left for questions. Thank you. I see a question. Cool.
So you have that picture of a brain and then a neural net and some outputs that go into like artificial limbs. Mm-hmm. Is it possible to put an actual limb on the other side? Like, what are the difficulties other than?
Oh yeah. So the question was like, hey, I showed that cool picture there, and there was like there's this sort of like neural netty kind of gap. It could be like a linear learner. Most of my stuff is like tabular. It's really kind of boring. But I mean, whatever that box is in the middle, the question was, can you actually then put a biological limb on the other side? And the answer is yeah. So the functional electrical stimulation demo, like that very small slide I gave at the beginning, was effectively just that, which was, and there's also work by a number of colleagues here and also internationally to say, provide devices, neural nets or other adaptive controllers to say, be the bridge across a part of a broken spinal cord. And so this is inherently exactly that problem where you're saying, like, I'm going to try to bridge a gap between my centralized control and a downstream biological part. There's one more, I'll give one more answer, might answer your question, is that there's also some cool examples other groups have done where they've had like one rat running around in a maze, and it has a BCI, a brain-computer interface, and its cortical patterns are mapped to another rat in another continent who's trying to solve a problem. And the rat in the one country, the whiskers, the sensory data from its whiskers hold a core component for the other rat solving the problem. And the other rat can learn to build out cortical representations of that rat's whiskers so it can solve the problem in that other country. Is that online, or do you have another part of it?
Follow-up is, how do you do that without trial and error? How do you know the signal that you'll give it will not damage something in the limb?
Yeah, and the answer is you can't probably tackle that head on. I think this is why when I'm arguing that it's very important that systems begin to learn the patterns of the data, it's also about us as researchers learning the patterns of the data to really truly understand our problem domains before we dive into them and then be able to structure it. I think, again, there may be a day, and I hope there's a day, where I actually get my universal glue. I can have a learning system that I can put between two systems, two intelligent systems of any kind. This works for the multi-agent folks. I see like James over there. It's like, oh yeah, maybe that'd be cool, but that we actually have some computational technology that can safely manage that full trial and error learning process. But for now, I think it really is very important to look at isolated connections and then start to expand outwards either ourselves or by way of constructive algorithms. Lots of questions. Let's go there and then back to there. And then I'll go pay attention to the other side of the room, I promise.
So most of the examples have been of human with some disability, and we try to help them out. So I'm wondering about the ethical aspects of humans with no disabilities and trying to augment their stuff. And I'm wondering, Spider-Man, Dr. Octavius kind of situation.
Yeah, so I mean, the question was, what about, and this is I like this question. I often get this question. I appreciate that because it means we're actually thinking about it, so thank you. The question was, well, it's one thing to try to augment the abilities of someone who has lost an ability. Someone with an injury or a disease or an illness, we may try to restore what they have lost, but those same mechanisms could arguably be applied to adding functionality to the folks that we have here, or one of those people that may have, like, we have a go-go gadget arm in the lab, a prototype, where someone with an upper limb prosthesis amputation might be able to extend out their forearm. I could never do that with my biological limb, but it's something that could actually happen for someone who's lost their limb. Now, there's all sorts of tech that could be applied. We have a prosthetic falcon as well. It's currently on a shelf, but imagine, instead of having a limb, you could just, like, throw a little quadcopter across the room and pick up, like, your iPhone or something and bring it back to you. So those are examples of augmenting someone that might have an extra opportunity for it, but there are also many opportunities for extending the abilities of someone who did not have it. There's like exoskeletons are being used in factories right now so that people have less lower back injury, that they can lift heavier loads. Like, we're already seeing, that's just one example of many, many possible augmentative technologies. And the answer is that we as a species don't really know what to do about it. We've always used tools. And often when people come up with new tools that make themselves better able to perceive the world, to act upon the world, or to think about the world, is that often has gotten us in pretty sticky situations. And so I think the answer is that we have to think really hard about this, and we all have to think really hard about this all the time. Because even if we're building, like, I don't know, if someone's building a GAN or someone's building another kind of technology that may not be actively applied to those kinds of domains, they're probably going to be applied in some way to augmenting human abilities. Like, everything that we're doing as a community, I think, is in some way augmenting our abilities. And we have to think really hard about that. I don't actually have an answer. Does that help? No, it doesn't. You're like, no, you have no answers. This clearly doesn't help. That's useless. All right, I saw someone yeah, there is, that gentleman there. Let me run up. Sorry, I'll run up. I'd like to be able to hear your questions.
Yeah, so it seems like there are like three parts to this. One is that getting signal from the human body. Second is predicting what the human is trying to do.
Mm-hmm.
And third is like controlling the prosthetic to actually get that action.
Yep.
So how difficult is the first part, and getting the signals from the outside of the body in like a non-invasive way?
Mm-hmm.
Do you think if we get invasive, it's going to improve the technology overall, or it's morely about the last two parts, and that problem is not, it doesn't matter too much?
Yeah, did everyone hear the question? It's really about like what's the importance of how we're acquiring the information, whether it's non-invasive or invasive. Is it what we're doing downstream with the information or the quality of the information itself? I'll sort of jump back. I think it was maybe, Nathan, was this your candidacy exam? We talked about like the 4 objectives of science. Yeah. So, I mean, this was a cool question. You answered it really, really well. And so I'm just going to paraphrase your answer in really words form. But I mean, what are we doing with our science? One thing we might do with our science is to describe the world around us. Another is to explain the things that we have seen. Another is to predict it. And finally, it's to control. These are some of the objectives of science. It is ambitious enough to simply be able to describe the signals coming from the human body. A massive amount of work is being put into this right now. It is incredibly ambitious. It is something that is not yet solved. So even just getting signals out of the body in a reliable way that is consistent, that could someday be used for a learning machine, that's really, really hard. Whether it's from the surface of the skin or directly from the brain or the spinal cord or what you're typing on your phone, these are all different ways you might get information out of that relates to the human will or intent. Really hard. That's already a very important problem. So solving that is something that we should tackle. There's technologies we have that in fact will relate to solving that problem. Assuming that we have parts of that problem solved, we can step to the next problem. And so whether we're non-invasive or invasive in terms of our recording technologies, there's some aspects that are highly fit. They're the operational level. They're like, how do we actually implement this, where the metal hits the tissue? And that might change. But there's some core principles that will hopefully relate to both those, the computational aspects or really the algorithmic aspects of that problem, which I think are very similar. And so in that case, a lot of the work that we've been doing has relied on non-invasives, largely because that means we can actually play with them. We can iterate really quickly. I don't have to wait for 20 years before we can actually try it out. We can have participants from the clinic come in, and like one of our recently graduate students, Dylan Brenius, he had an idea with the occupational therapist from the Glen Rose Hospital about a prosthetic limb that self-levels. So as you're walking around with your coffee, you don't spill it as you move. So it's a simple idea. He was able to come up with the idea with the OT, get it ready, in a sense that he could prototype it, move through it, and get it to where we could actually use it with someone with an amputation. We're at that point now, in under a year. So that's a very fast design cycle. So we've chose to place ourselves in an environment where we can tackle the core problems. We are not bottlenecked by some of the fundamental problems, which aren't the things that I think I need to solve right now, at least, and still make really rapid progress. So you can choose where you go on that particular continuum of describe and explain and predict and control. I think there's all good choices. There's no bad one there. It's just what you want to focus on. Oh yeah, this side, please. Yeah, so I think, so the question was, we have our typical control loop, we have feedback. Feedback is totally normal. You make actions, something happens, the system perceives those. And I think the answer is that the feedback path, I showed that original slide where there was the person and the machine and the control system. There's many different feedback loops in that system. Some of these feedback loops are like visual loops where the person actually perceives the technology doing something. That's one feedback loop to the person. The machine has similar feedback loops. And so what's interesting is that there is still going to be a closed loop motor control aspect to this particular paradigm, especially in the work here, because the person is very intimately connected with the feedback. The nice way to nestle this approach into a standard, say, control loop setting, and I think this is one that actually has great utility, is in fact by treating some of those predictions as simple observations that just go into your usual control loop. So if you have a very good idea of how your control loop functions, how your feedback path functions, you can begin to look at receptors. Essentially, instead of having like 15 sensors and then put them through and then use predictions somewhere in the middle to modulate that loop, maybe without the feedback actually being able to control how those predictions are gated. You could also just think of like, well, we could just use the predictions as additional inputs. Treat them like sensors. Don't even tell the system it's special. And the system will then begin to have forecastive, it's not even a real word, predictive inputs as sensors. So it's a perception. A perception is based fundamentally on prediction as well as on direct observations. And that way, it sort of dovetails into that same feedback loop that you might have otherwise. Yes, please.
Hello, I'm Spy, so I think I'm in as well. A lot of the videos you showed of BCI, of the prosthetic limbs at least, seem to be controlled by EMG or sort of sensors of muscles that people already had. How well can we get these sort of fine-grained controls of robotic limbs using actual BCI purely based on brain signals?
So the question was, like, a lot of the work I showed was based on what was called myoelectric control. So the idea is that you're sampling signals from the muscles. When muscles do their job, they create electrical activity, and then that activity can be monitored and used to control a device. That's the current the dominant clinical mode that we see people with myoelectric prostheses using. But then the question was, well, we also can stick wire. I'm paraphrasing poorly your actually elegantly worded question. We can also stick wires into the nerves. We can stick wires directly into the brain. And I mean, some of you probably saw the big Neuralink announcement recently. You can even put in all these nice little flexible electrodes. How good can we do with that? And so I think the first video I showed, where you saw Jan Schuerman with those two implants, Jan was able to do some fairly reasonably complex motor control. I think that is better now. So what you saw there, it was a good first approximation. Folks like Dario Farina have done some really cool recent work looking at decoding directly from the peripheral nervous system. So let's imagine we go a little bit back from the central nervous system downstream here, looking at ways to use the physical body or the physical system as a decoding model for the time series pulses going down bundles of peripheral nerves, and actually getting pretty spectacular coordinated fluid motions by using their models of the physical system to decode the time series of neural spikes. So Dario's got, that's just one example. That really struck me. I saw that a couple years back at a conference. And it's just one example, but the videos he showed of people using this neurotechnology, like they have people with that actually implanted. Like I think it was clamp electrodes as opposed to interdigitated electrodes inside the nerve itself. But either way, they were getting these really nice coordinated multi-joint motions, not to the degree you could spin a pen, but all of the joints of the wrist and the opening and closing of the hand were very nicely coordinated using that approach. So I think there's been, especially our colleagues in Europe are doing some pretty good work on that. There's a bunch of programs in the US as well right now that are looking at like high density direct recording from the brain, a lot of them wirelessly. And so I haven't seen them demonstrate specifically that they can do really powerful coordinated fluid motion, but my feeling is that the information is there in the data to make that possible. Cool, thanks for the question. I've got 3 minutes according to this big clock here. One more question, or should we? Oh, yes, please. Sorry, I can't hear you. I'm going to run up here instead. Oh, okay, great. So this was a question about, this is a question that's much more suited to my clinical colleague, Jacqueline Hebert, than me, but I'm going to try and answer it anyway, and I might be wrong. So the question was, what's the typical cost of, I think you mean one of the prosthetic systems and the procedures related to it when someone is fitted with a myoelectric prosthesis. Is that a good paraphrase? So in some cases, like when we look at someone getting fitted in the clinic for a robotic device, an electromechanical device like some of the arms that we see, the clinical devices, a hand might run you anywhere between 30 and 50K. A full arm system might be anywhere up to 120K, and that's not counting some of the clinical costs as well. And so a lot of the devices right now are prohibitively expensive. There's a lot of movements now. There's Project Daniel, there's the Robot Hand project. There's many projects now that are looking at inexpensive 3D printed open source approaches, especially for countries where it's not possible to deploy some of the more expensive technology. But right now, this is one of the barriers. The clinical cost is quite high. Part of that is the other part of your question, which is how many people are actually using them. And the incident rates for upper limb amputations are actually a lot lower. So a lot lower limb amputations are quite common. The devices are, I think, less expensive, although I'm not an expert in the lower limb. But lower limb systems are fairly far down the path of optimization compared to upper limb devices. There's maybe, I'm looking panically around the room for someone who's on one of the papers that knows this better than I do. Nope, that's not, it's gonna be me. Maybe there's 200,000 or 300,000 new examples of upper limb amputation in North America on a yearly basis? Or is it 30,000 and it's like 300,000 right now, people that are using an upper limb device? Anyway, it's not on the order, I don't think it's on the order of millions. So it's quite small compared to other, compared to rates of heart attack and things like that. It's incredibly small, which is why the market for it is not facilitating a real pressure to create inexpensive devices. So cost is a really big barrier. Standardization of devices, typically because of that, there aren't custom fit devices, like mechanically custom fit. And so that's something people are tackling right now as well. Again, don't quote me on the numbers. If you really want those numbers, I actually know the papers and the right people to talk to, and it's not me. Thank you. 41 seconds left. Yes?
So when you use like brain signals to do a movement and move a robotic arm, for example, how much one model is transferable to another person?
Ooh, I like this question. It's going to take me more than 25 seconds to answer. I'm not going to apologize to Cam. Not apologizing. Okay, I may be apologizing a little. I'm sorry, Cam. The answer is what's transferable, what isn't. And so there's a couple of points. That's why I said it's going to take longer than 25 seconds to answer, is that there's a couple of things that dovetail together. One is that for any given person, some of the literature has shown that if you train a classifier on brain signals today, and I put you in the exact same experiment tomorrow with the exact same classifier, that classifier won't be that great. So even our own brains are non-stationary to a massive degree. So those of you out there that are working on non-stationarity and learning and adaptive systems that will change over time, yeah, we really, really need that, because even for individuals, your own use of a system will change over time, both in terms of your brain patterns, the way the brain is adapting to the physical hardware, and various other factors. So that's one thing. Between people, there's some things that are very nicely consistent across people, especially for myoelectric control, let's say. Let's go outside the brain, go a bit farther downstream, is that most people, even after amputations, largely have their muscles in roughly the same places. And even if you're going right into the bundles of nerves, those nerves are sort of consistently routed to bulk regions of the brain. So there are some things that transfer over. There's some cool work there's a paper by Tomasi et al. In 2013 that looked at building up classifiers for downstream myoelectric control and seeing that they could actually, have 100 people build up classifiers for all those 100 people, and then when someone new uses the system, be able to fuse those together to create a new classifier that can then be optimized for the other person. And the reason that work actually was successful is that there are elements that transfer across people. Finding those elements, or maybe it's even finding the meta-learning technologies that allow rapid adaptation to new individuals, are something there are consistencies between different forms of biological processing. And so, yeah, we should be able to find systems, whether it's a certain classifier or it's a meta approach to rapidly develop classifiers, discriminators, regressors, interfaces. Either way, there will be regularities. It's just the question is what level should we be finding those regularities? And now I really am out of time. All right, thanks again, folks.